Welcome everybody. I'm not going to introduce the speaker, but I'm going to introduce a new visitor, Sandu Popescu. Sandu will be here for about a month and something. Yeah, something. A lot of you know Sandu, and so those who don't, I advise you to find out. Talk to him. Okay.
All right. Hey everyone. So today we're very happy to have Dave Jacobson from the University of Maryland, and he's here through the day. So if you have questions after the talk, you'll be the right time to ask them. And he will discuss horizon entropy, entanglements, and Einstein's equation.
Hello, thank you for having me. I've actually never been to Stanford before, and it's a beautiful campus. Okay, so I thought
We hope you'll come again.
I'll start with a prologue. It's a little bit historical, and it's because I started reading an amazing book by Thomas Kuhn called Blackbody Theory and the Quantum Discontinuity, 1894, which is the year that Planck started started working on the problem of radiation and equilibrium. And I'm not sure what 1912 is yet, because I haven't finished the book. But I just wanted to say something I didn't realize is that what was Planck doing when he started working on this problem? The reason I'm bringing this up, this prologue, is just that I feel like it's the right context to think about why do we worry about crazy things like black hole thermodynamics and information paradox, and what could we possibly learn by thinking about that? So Planck was worried about the second law. He wanted it to be as fundamental as conservation of energy. And the problem was there was no way to account for it with an atomic theory of matter that behaved according to the laws of classical mechanics. And he got the idea that the new theory of electromagnetic fields was going to solve the problem. And because somehow there would be irreversibility inherent in the absorption and re-radiation of energy from the field by the particles. That was what he was motivated by. And so he figured he should look at the problem of thermal equilibrium of radiation with matter. Of course, he did find out pretty quickly that that was a foolish idea, or a wrong idea, let's say. But he found something much more interesting than the problem he started out trying to solve, which is quantum mechanics and quantum field theory. And then Bekenstein, in 1972, set out to save the second law from black holes, in the sense of save it from irrelevance, because if you could just dump entropy into black holes, as long as you live outside the black hole, the second law would sort of be inoperative for you. And he used the information theoretic notion of entropy to infer that a black hole should have an entropy that goes like its area in Planck units. And he thought he had solved the problem that he set out to solve, but he fooled himself. The second law actually wasn't saved yet. And in fact, his own arguments would have led him to infer the existence of thermal radiation from a black hole, but he didn't take that step. I think fundamentally the reason is probably a combination of being browbeaten by his elders, who were not very receptive to the idea that a black hole had a meaningful temperature. But also, he probably wasn't thinking about quantum field theory very much, because if you take a black hole and immerse it in a quantum field, sort of the arguments that he had given essentially led to the idea that it should have a temperature, but he didn't make that connection.
But you didn't really need the quantum field theory. You just consider it as an energy and as an entropy. And dE equals TdS.
Yeah, but that was the kind of naive argument that his elders objected to.
Yeah.
You could really argue that the second law would not be saved unless it was actually radiating. Anyway, this finally led to another paradox, which is the black hole information paradox. If the second law worked apparently too well, because entropy really was increasing outside the black hole. And yet, for other reasons, at least in some theoretical settings, there's reason to believe that entropy, fine-grained entropy, is not increasing outside the black hole, and we're left with that puzzle today that hasn't yet been solved. How to have the second law and at the same time have unitarity. So this is a form that we're currently puzzling over. And we continue down this path, puzzling over the fundamentals of entropy and information, with every right to expect further insight as it has happened before. We hope, as we drift further and further from data. So the other thing I just want to mention about this book, I learned that Planck solved his problem along the way. So he thought, when he actually managed to derive what's called the beam distribution for radiation, which applies to the high frequency part of the spectrum. And he succeeded at that point strictly on classical arguments and thermodynamic arguments about entropy. And no sooner did he succeed than more data came in on the infrared part of the spectrum, and his calculated beam distribution didn't match actually the data. And it was that forced him back to the drawing board. And he finally, as everybody knows, came up with he figured out what was wrong in his previous reasoning, made a guess at the new form of the second derivative of the entropy function. It matched beautifully the data, and then he, in order to find a theoretical justification for that form, he had to partition energy into quanta just in order to apply Boltzmann's counting. Not at all what he thought he was doing when he set out. Okay, so that's the prologue. Now I want to switch to general relativity for one slide and just talk about strictly classical general relativity. I don't know if you know that the classical vacuum Einstein equation can be stated as follows. That if you take any small ball anywhere in space-time, by ball I mean a geodesic ball generated by launching geodesics out from one point in space, orthogonal to a particular time-like vector. Any small ball of a given volume has the same surface area as it would have had in a flat space-time. That is the Einstein equation, exactly. And for vacuum. If there's matter, then there's an area deficit if the matter has positive energy. And the deficit is proportional to Newton's constant times the energy inside the ball times the radius of the ball. This was a picture to show what I mean by space-like geodesic ball. Some of this stuff we need later, but here's the point in space-time, time-like vector, it's a space-time diagram, and these radial lines are the geodesics, and they go out to some radius, which I'm calling L there. So that's a geodesic ball of radius L, and I'm assuming, for the statement I just made, that the ball is very small compared to the length scale of the curvature. This stuff will become relevant later. I'll come back to it then. So mathematically, precisely what is this statement about area, deficit, and curvature? Well, if we hold the volume fixed and vary the area, then it's proportional to minus the Ricci scalar of the three-dimensional geometry that's swept out by those geodesics, with a particular numerical coefficient that actually will be important to me. It goes like the length to the d power, where d is the space-time dimension. This is just the area on a d-2 sphere, and then some numbers. But then it's also true that actually this Ricci scalar is equal to the 0, 0 component, actually maybe twice that, of the Einstein tensor. And this is then connects to the Einstein equation. According to the Einstein equation, that's the 0, 0 component of the stress tensor times Newton's constant. And so you see that we get a connection between area deficit and energy inside the ball. Just note, here I'm holding the volume fixed. It's sort of clear we should hold something fixed. Maybe I should have held the radius fixed. If I hold the radius fixed, then the variation of area is not the same as the variation at fixed volume. They differ by a d+1/3 coefficient. And that distinction will actually be important. So it'll turn out that by the end of this, we see the Einstein equation emerge from the principle. I won't say what it's going to be, but it wouldn't emerge with the right horizon entropy if I had used the fixing of the radius principle. You have to hold the volume fixed, and I don't really know why. I don't have a fundamental rationale for that. Maybe one of you can explain it to me. Okay, so now I want to rewrite that Einstein equation in another form that's going to connect us to ideas of quantum mechanics and eventually to the entanglement in the vacuum. So the Einstein equation we just had was the area deficit is minus Newton's constant times the energy compared to the vacuum. So that's what I mean by delta E. I'm comparing the area in vacuum or in flat space to the area in this space-time that has energy in it. And this was the formula that we just got. Maybe I don't want to lose you on that little trivial point. So this is L to the D power. If we multiply energy density by L to the D minus 1, we get energy, and there's one L left over.
This is related to Bekenstein?
Oh, it's about to be, yeah. So now let me just take this equation and divide both sides by h bar times Newton's constant. So on the right, I'm going to get delta EL over h bar. And on the left, I'm going to get basically the variation of the entropy you would associate with the boundary of this ball if you're using the Bekenstein-Hawking entropy. So this is saying that the boundary, the entanglement entropy, if we interpret this Bekenstein-Hawking entropy as vacuum entanglement due to the entanglement of vacuum fluctuations, this is saying that there is a link between the variation of that entanglement entropy and some other quantity which, which involves the variation of energy and Planck's constant. What is the meaning of that quantity? Could this equation arise from a fundamental principle without assuming gravity, as I just did here? And the proposal is yes. The principle is the vacuum has maximal entanglement entropy. So that's written here that if you fix the volume, the vacuum entanglement in any small ball is maximal. And I'll show you that under some assumptions this works. This really is equivalent. This does imply and is equivalent to the Einstein equation. So first let's ask, is it even plausible? Because recently I gave a talk on this and somebody objected. How can it possibly be true that the entanglement is maximal in the vacuum? I mean, they said, in condensed matter systems, an area law for entropy is a big exception. The puzzle is why doesn't it go like the volume? How can it possibly be maximal in this ball? And why can't I just put more entropy in it? Take a particle that's entangled with another one and stick that particle inside the ball. So suppose we did that. Well, quantum mechanical uncertainty implies that the energy associated with that particle localized in the ball times the radius of the ball over h bar must be greater than 1. But by the Einstein equation I just showed, that means that the area deficit in Planck units must be less than 1. Now, I'm going to propose that the net entropy, well, what is the entropy of this ball? It's the surface contribution that comes just from the vacuum entanglement. And then if you manage to put something else inside it, well, yeah, you could have kind of bulk entanglement from the excitation of the state. And you should add the two together. But this is saying when you add them, the area part decreases by more than the bulk part increases. And so overall, actually, the total entropy goes down. So it looks like it could be consistent. That is correct, that the entropy is truly maximized in vacuum. You could worry, what about if instead of putting a particle in that had like a qubit worth of states, what if I had a highly entropic system? And that was something that's actually been worried about in another context by Merrill and Sorkin and Merrill, Minich, and Ross. And they showed that, basically they noted that actually that doesn't help. Because if systems exist in the world that are highly entropic, like say a particle that has a huge number of internal states that are all degenerate, then the vacuum contains the field that corresponds to that particle, and the vacuum entropy also is increased by a huge amount because of all those states. And therefore, actually, there's a dilution effect when you try to put that particle in. You're not actually going to increase the entropy more. In fact, you'll be offset by the increase of the thermal, quote-unquote, entropy of the vacuum inside the ball. So it's really not a crazy idea.
Do I need to worry about how you're going to define the spatial volume of the black hole?
I'm not even talking about a black hole, so I
you
think
just
the answer is no.
perturbative?
This is a small ball.
Yeah.
It has to be smaller than the radius of curvature of space-time.
Okay.
And actually, it's going to have to be smaller, this is a good time to say it. If I excite the quantum state, I want to make sure that the ball is smaller than the wavelength of any excitation. So I'm deep inside of that. And it should also be smaller, it'll turn out, than if the quantum field theory is a conformal field theory, then I don't have to add this. If it's not a conformal field theory, that's actually an uncertain part of the argument. It may not work. But if it does work, it has to be only when you take the ball small compared to any length scale in the quantum field theory.
Any length scale.
I think so, yes. This is the part of the argument where it trails off and gets a bit ragged at the end, I hope. I feel like since it works so nicely for the conformal field theory case, probably it works, but maybe only with a more precise set of ideas. Okay, so here's the setup we're going to ask. We're going to consider the ball as I just described, and we're going to consider the vacuum with the vacuum of the quantum fields and the geometry being flat space. Later I'm going to have to switch to a maximally symmetric space as equilibrium geometry, which I think makes sense. And we're going to consider variations away from that where the metric varies and the quantum state varies. So this is a semi-classical setting where we have well-defined geometry and quantum fields in the background. And I'll decompose then the entropy, like I just said earlier, into what I call the UV part, which is the area contribution, and the IR part, which is just the bulk inside the ball. It's not very IR, but compared to the boundary term it is. And I'm going to assume that the UV part is just proportional to the area variation that we just discussed, with a coefficient of proportionality that's just supposed to be a fundamental constant of nature. Ultimately, it might actually be 1, and we just define the metric in terms of counting entanglement, but that's another matter. And then this IR part, we can write as the variation of the expectation value of some operator, where that operator is the logarithm, or minus the logarithm, of the vacuum density matrix inside the ball. So the idea of this is that, so any density matrix could be written as e to something, and if you write it that way and you look at it, it looks like the Boltzmann state of some thermal distribution if you just pretend that K is the Hamiltonian over the temperature. And then we're familiar with the fact that the variation of entropy in equilibrium is just equal to the variation of energy divided by temperature. So in fact, the variation of entropy when you vary this state will just be the variation of this operator in the logarithm, in the exponent. The catch will be, okay, what do we know about that operator? How do we describe this thermal state? And we'll get to that momentarily. It's called the modular Hamiltonian for any quantum field theory. So it's the modular Hamiltonian associated with this region.
Sorry, I have a question. So the argument that you made for the vacuum entanglement to be maximal, why couldn't I make it for any other state that's not the vacuum? I could make the same argument precisely. I add a bit, the area goes down. The vacuum played no special part in that argument. Or did it?
That's interesting. No, it did, because the formula for the variation of the area is for variations away from flat space. Or actually a maximally symmetric space, I'll also use it. So
the formula connecting the entropy to the area?
The formula connecting the variation of the area to the curvature of the space-time. So it had to be that I was varying away from the flat case. I compare the surface area in the flat case to the surface area in the curved case, and I got that formula. So by invoking Einstein's equation, I had to be talking about a state that was near the vacuum, and I'm just comparing it with the vacuum. But let's talk, maybe I haven't fully appreciated the question. I'd like to, before going on, pause and ask, why is eta not infinite? So we're talking about the entanglement entropy across a surface. In a quantum field theory, there are an infinite number of UV degrees of freedom. If I just have a field theory in a fixed background space-time, it has an infinite entanglement entropy. And yet, I won't get anywhere with this if I let eta be infinity. So I could just say I'm assuming it's finite, but I just want to anticipate the connection to gravity by giving you an argument that, I don't know, maybe it's so, I haven't heard anybody give it, but I'm sure that everybody gives it all the time. But since I never heard anybody give it, I'm going to give it. So the question is, why, and then parentheses, in a theory with gravity, is the vacuum entanglement entropy not infinite? So why is it finite? So we consider a spatial slice divided in two halves, and I just drew these light cone lines because they're suggestive. And think about the vacuum entanglement entropy. It comes from vacuum fluctuations like A on this side being quantum mechanically entangled with fluctuations on that side, A tilde, similarly B with B tilde. And the question is, as B and B tilde come closer and closer together, is there some scale at which I should stop counting their entanglement? And if so, because of gravitational effects, what would the nature of that be? The argument is simple, in fact, that if you localize this pair of vacuum fluctuations to a size LC, then there's some energy uncertainty associated with that h bar over LC. And if we plug that into the gravitational field equations, we find that gravity is strong at this scale. In other words, the LC is smaller than or equal to the Schwarzschild radius associated with this delta E, the gravitational radius, when in fact LC squared is less than L Planck squared. I guess I did this in 4 dimensions. So in other words, as soon as LC gets smaller than the Planck length, there's a very strong gravitational reaction there. The causal structure, like we could make a little black hole or something, the causal structure of space-time is not well defined. And so the subsystem we're trying to define the entanglement entropy of becomes blurry. And therefore, it would be kind of meaningless to try to say that on the right-hand side, we have extra entanglement entropy because of the entanglement of B with B tilde, because we don't even know which side they're on, okay? Or even if there's a well-defined geometry. And notice that this cutoff is Lorentz invariant, because the entanglement of pairs is, I'm not talking about the distance of some object to a horizon, to a surface, which would depend on the frame and the surface that I drew. The pair is intrinsically a property of the vacuum state, and so it has its own natural distance between the things that are correlated. So I think morally this is the reason, if you have gravity, the entanglement entropy can come out to be finite. Okay, so let's try to now implement the idea. The task at hand is to evaluate the variation of this modular Hamiltonian. Remember, that's the contribution to the bulk entropy from changing the state from vacuum to something excited. So if we had been in the Rindler wedge of Minkowski space, that is just, which is the part of Minkowski space visible to uniformly accelerated observers, we would have the famous Unruh effect, which is the fact that the vacuum looks like a thermal state in the Rindler wedge. And the Hamiltonian for that thermal state is the generator of Lorentz boosts in the wedge. And the temperature is just h bar over 2 pi. It has dimensions of action because the Hamiltonian has dimensions of action because it's a generator of boosts, which is like an analytic continuation of rotations. Now, if we have a conformal field theory, we can use the fact that a small ball is conformally related to an infinite half space. And in terms of space-time regions, we have this, here's our ball. We can look at the causal domain determined by the ball, and it's this double cone thing or diamond. And the interior of that diamond is conformally related to the entire Rindler wedge. And if the field theory is a conformal field theory, therefore we can just map the field theory inside this diamond to the Rindler wedge, and in the Rindler wedge we know how to calculate the variation of the entropy because we know exactly what thermal state we're talking about. It's the one generated by the boost generator. So that's what actually Hislop and Longo, in a very different way of thinking about it, realized a long time ago in 1982. Cassini, Huerta, and Myers recently spelled it out for conformal field theories in general and derived a lot more than that. So this is the formula it gives you then. We've got the energy thing, which is what I call the conformal boost energy. We have a local stress energy tensor expectation. CA is the conformal killing vector that preserves that diamond, so it flows up the edges of the diamond and then down to the vertex of the second cone and flows through the middle of the diamond. And the formula for it is here in terms of R and T coordinates. I'm not sure what you can get out of that. It's nice to look at it in U and V being retarded and advanced time coordinates. It has a very simple form. But it's just the unique spherical conformal killing vector that preserves that double cone. And so that's the thing that's conformally related to the boost in Rindler space. And so we just basically look at that component of the stress tensor. This integral becomes the Hamiltonian that generates that flow, and the variation of it is the appropriate thing divided by the temperature to give us the variation of entropy. The temperature, though, is just the unroot temperature, which is h bar over 2 pi, so I have a 2 pi over h bar. Now I'm assuming my ball is very small. This is where it becomes crucial that it's small compared to any wavelengths of the excitation. So I can treat TAB expectation value as constant inside the ball. So it just pops out as an expectation value, and I'm just left doing a geometrical integral of this component of the Killing field over the volume of the ball, and this factor is what comes out. So now you can see we're almost to the Einstein equation because, well, let's not anticipate. So here's how we get to it. This is just repeating what I just said for the variation of the modular Hamiltonian, which gives us the bulk variation of entropy. Delta A at fixed volume is going to give us the boundary variation, which we already knew is related to the Einstein tensor, with a particular numerical coefficient, which looks very similar to that, but came from a completely different place, because in this calculation I have a conformal boost killing field that has nothing to do with this calculation. And now the principle, remember, was that in vacuum the entropy is maximized, and that means if I compare a nearby state to vacuum, the entropy should be unchanged to first order. And so I'm going to set the total variation of the entropy at fixed volume to 0. That means that eta times this plus this should be 0. But then you see immediately I just get the Einstein equation. Well, this is for one particular frame, the not. But I'm assuming that this same relation holds for any fixed small geodesic ball launched orthogonal to any time-like vector. So I get all different projections of the Einstein equation, and that tells me that as a tensor equation, the Einstein tensor is proportional to the variation of the stress energy tensor, and the coefficient is just 2 pi over h bar divided by that eta, which gave us the fundamental entropy density of the vacuum. Now, if we just compare this with the Einstein equation, we see we can write this as 8 pi g, provided that eta is 1 over 4 h bar g. Because, yeah, I'll just divide both sides by 2 pi. But this is the familiar entropy density that Bekenstein-Hawking entropy has. So it turns out to be consistent. I derived that the geometry must satisfy this relation between curvature and energy density. And then, with a particular Newton constant, and the value of that Newton constant is such that when I re-express my entropy, surface entropy in terms of it, I get the Bekenstein-Hawking entropy. If I had used instead the variation of entropy at fixed radius of the ball instead of fixed volume, remember that factor that I pointed to at the beginning, I would get a different coefficient here. And instead of getting the Bekenstein-Hawking entropy, I would get something else. That would actually be wrong, strictly wrong, because we know you can derive the Bekenstein-Hawking entropy just from quantum field theory in curved space-time and the Unruh effect. So that can't be gotten around or modified. So there's something correct about this principle I'm proposing with fixed volume and not with fixed radius.
So there's something very puzzling. Why are you restricted to a conformal field? This is a conformal bulk field theory now.
Yeah, I'm about to...
I understand why you want the volume or the radius to be smaller than any excitation in the system.
Right.
But this would, as you said before, this would require you to take the radius to be smaller than any microscopic scale.
Right.
And surely it can't be restricted to that.
Right, so now let me try to extend it
Oh, okay, good.
to general quantum field theory. So I have to make a conjecture here, and it's being investigated by various people, but it's not clear yet whether it's true. And the whole thing I'm going to say now hinges on this conjecture being true. And the conjecture is this, that when I have a field theory that's not a CFT, provided I'm looking at entanglement entropy in a ball that's small compared to all these scales, that the variation is the same coefficient and the variation of the stress tensor component plus the variation of some scalar operator. Has to be a scalar, so there's no tensor indices on there. I don't care what operator it is. Initially I thought it would be proportional to the trace of the stress tensor, so that what would come in here is the trace-free part of the stress tensor. But that seems to not be true based on this work that Damian Galante and my student Anthony Speranza have looked at. So I think it's definitely not true that I know it's definitely not true that it's the trace-free part. I think it may not even be just the trace, although the trace appears. But like if you deform the CFT by a scalar operator, that can come in also here. But let's just suppose now with me, we just conjecture that this is true for some scalar operator.
A local operator?
Well, the whole thing is sort of local because the ball is so small that it's effectively a point as far as the state is concerned.
K is something not local in general, right? The reduced density.
Right, but this is...
That's a special thing, the CFTs and
Right, but remember we don't need to... All that matters for this calculation is the net variation of the expectation of K. So K fundamentally is the non-local operator in the ball. We're considering a certain class of states for which the ball is very small. We finish doing the integral over that ball. The final answer is supposed to be this evaluated at the center of the ball. So let's say this is true. Then how would that modify the calculation I just did, the derivation? So then when I put in the variation of the entropy, I won't have just the stress tensor, but I'm going to have some correction term coming from this x. And this looks really bad because of the Bianchi identity. So the stress tensor is conserved, and we have the Bianchi identity that G has zero divergence. We conclude that this x operator must be, the variation must be constant in space-time. And that's clearly unphysical, like if it were the trace can't be expected to be a constant.
But you've already assumed that all the excitation length scales are longer than the size of the ball, so why can't it be true?
Because this would have to hold at this equation, so I've looked point by point at space-time, and I claim to have concluded that this holds as a tensor field equation.
Okay, so you say it's comparing different balls at different places.
Yeah, exactly.
Thank you.
So this is over-constrained, so this can't be correct. And thinking about that led me to think, well, what did I do that was too rigid? And what I did, I think, was I assumed that my equilibrium the vacuum equilibrium state that I was comparing to was flat space. But actually, any maximally symmetric space is equally good candidate for an equilibrium system. It's isotropic and homogeneous. And so I would like to, instead of comparing to flat space, compare to a maximally symmetric space, which means like a locally de Sitter or anti-de Sitter, which is characterized by some value of the cosmological constant. Now, which value? Well, I don't know a priori, so I'm letting it float. It just has to be that there's some, at each point, there's some value of this local floating cosmological constant I can choose, such that when I compare that, when I make the variation of the entanglement entropy compared to that vacuum, the variation is 0. So how do I implement that? Well, it's just that when I put in the formula for the area variation of the Einstein tensor, I should subtract the Einstein tensor of the maximally symmetric vacuum. And that actually means I should add some constant times the metric that's the local cosmological constant, which I'm calling lambda. So if I do that, what equation do I get? So on the left-hand side now, I have two changes. I have this correction with a delta of expectation value x, and on the left, I have an extra term that's some lambda times the metric locally. Now I impose the Bianchi identity, and I find that it's perfectly, instead of finding that delta of x has to be a constant, it's the sum of that and lambda that has to be a constant. And that's no problem because lambda was just a floating local cosmological constant anyway. And so this determines the sum then of these two up to some constant that's unknown. So if I then write this equation in terms of that constant, I just get the Einstein equation with an undetermined cosmological constant, capital lambda. Wait, what time is it? Oh,
Wait,
yes. I better go back.
It's not a question of the formulas. What does that do? That is just some floating cosmological constant that you put in. But you're not assuming that that's some cosmological constant of the theory itself.
Right. I'm only saying
What does it mean?
it means that the state I'm looking at should be viewable as near a local maximally symmetric space with some vacuum of the corresponding vacuum of the quantum field.
why is that so?
Maybe it's not. It's the only thing I can do.
Oh, okay.
I think it's sensible that I shouldn't prejudge what vacuum looks like, this microscopic vacuum, the equilibrium state that I'm comparing everything to. So the idea is that somehow the true quantum gravity vacuum reaches local equilibrium. But depending on what matter is there, that local equilibrium may be like that of a local maximally symmetric space that's not flat. I don't know.
But it's not, but that lambda is not the lambda that we would associate with cosmology or whatever.
Right, let me emphasize this again. So that lambda, for this equation to be consistent mathematically, has to have the property that when you add it to delta x, you get a constant.
Right.
Therefore, that lambda is equal to the one we associate with cosmology minus this.
Oh.
That's the best way to see. Maybe there's another way to do this. And now, the bad news. So I guess you thought that was already bad news. But I don't think it's too bad.
It's puzzling.
So here's what might be a real problem with it. Not all energy manifests as entanglement entropy. In particular, consider coherent states. So this part, I don't think I have any slide prepared. I just want to explain it. Maybe we should turn the lights on. So imagine we take the vacuum on some spatial slice and excite the quantum field to a coherent state. Remember, in quantum mechanics, a coherent state you can get by acting with like a dagger. Let's make it anti-unitary times some parameter acting on the vacuum. So for a harmonic oscillator, we can apply a unitary transformation to the ground state and get some state that's not the ground state. And in a field theory, we can do the same thing. The key thing being that the exponent here is linear in annihilation and creation operators. So then we have a field that's a function of position. We could write down any kind of a thing like this, like e to the integral of field operator times some function plus, let's say, time derivative of field operator times another function. Let's say plus Hermitian conjugate, and I'll stick an I on so it's a unitary operator. And this thing acting on the vacuum gives us some non-vacuum state that certainly has energy density in it in general. And the problem is it doesn't change the entanglement between two sides of space, which you can see immediately from the fact that since this is linear in annihilation and creation operators, I can actually factorize it by splitting up the integral into the right-hand side and the left-hand side. And this operator just becomes an operator acting on the right times an operator acting on the left, both of which are unitary. And so unitary operators won't change the entanglement. Therefore, this entanglement hasn't registered, this energy has not registered as any kind of change of entanglement in this setting, and it won't in my setting of my little ball either, if the ball is what I'm talking about. And maybe I should have drawn a picture of the ball. Now, at first, it seems like this means that something I did was wrong, even at the level of the conformal field theory. Because you can certainly make a coherent state in a conformal field theory. For example, let's just take a free massless field theory that's conformal. And yet, there didn't seem to be anything wrong with what I was doing. What's the resolution there? And the resolution is that it's true that the variation of the entanglement entropy is equal to the variation of the sort of energy density, but they're both zero. Because if you think about the variation at first, if you're talking about first order in these functions here, then you've basically got first order in annihilation and creation operators, and expectation value of the energy density will not be shifted by sticking those operators in. So similarly, the entanglement won't be shifted. So it's not like there's a mathematical error or a logical mistake, but it's like maybe restricting to first order variations is too crude, and it's an inadequate representation of what it means, of the implications of having the vacuum be truly equilibrium. To go to higher order, I should include higher order terms in F and G. The problem is, for this particular state, I could go to any order in F and G, and the entanglement will be exactly unchanged, and I will have energy density. So,
Because you go to too higher order, then gravitational back reaction will do something.
yeah,
But that's probably not what's going on.
I don't see how that could. Now, it's true that this very simplified picture uses free field theory, and there's always gravity interacting. But I couldn't come up with a kind of general argument that shows that there won't be some residue of this problem. I guess my best guess is that what it is that, if the statement that the vacuum is an equilibrium state would imply that first to first order the entropy is unchanged. it would imply that to second order, the entropy goes down. And there's more information in that. In fact, there's a connection to the prologue, because Planck, one of his key principles he was following when he was trying to calculate the equilibrium distribution was the fact that the entropy should be maximized in equilibrium. And that told him that the second derivative of the entropy function was negative, and he used that in his calculation. I'm not using that in my calculation. I don't know how to use it. Everything I did in the calculation was sort of first order, and it became simple because I only considered first order variations. For instance, when I varied the quantum state, I didn't have to also consider the variation of the geometry. I could consider them separately because each one, they contribute additively at the first order. So there you have it. I don't think I have anything more to say to defend this idea, except that it just looks so natural and works out so well in the CFT case, unless you don't buy the, well, actually in the CFT case we don't even have this maximally symmetric space thing. So it works out very nicely, including that business about the coefficient that I mentioned. That could have been anything. It worked out to be the right one to match Bekenstein-Hawking. That it just kind of makes sense to me, but I don't have nothing else to say about it. So thank you.
So I have a question. So forgetting for a moment the connection between this conjecture about the entanglement entropy being maximized in the vacuum, the connection between that and gravity, to explore just the entanglement entropy being maximized in the vacuum. Is this to say that, say I have a completely non-gravitational field, I'm not going to worry about gravity, and I take the entanglement entropy for, say, an interacting scalar field theory, 1 plus 1 or 2 plus 1 dimensions or something like this, and I have say a one parameter family of states for which I have the vacuum and I can tune, say, the particle number. So the conjecture states, just if I understand correctly, that the entanglement entropy should be somehow increasing potentially, or at least that somehow if I increase this parameter around my vacuum state, that the entanglement entropy should go up locally or something?
Wait a minute, so there's two issues here. I'm only making the conjecture when there is gravity, because when there isn't, we have an infinite entanglement entropy in a quantum field theory.
But the variation can still be finite.
Maybe, yes.
In fact, it is in 1 plus 1
And
and 2
then,
plus 1. Scalar fields.
But I wouldn't anticipate it having a definite sign, that finite. I think the whole thing hinges on gravity being there.
So the only reason I asked, there was a recent paper in which, indeed, it appears to actually have the right sign which you spoke of.
That it goes up or
It goes
down?
up. It goes up.
See, I was saying, oh, sorry, the matter.
The more matter you put in it.
Oh, sorry, yeah, so if you change the state so that the energy density, remember the way I evaluate the variation of the bulk term, which is pretty much the variation you're talking about because the area term will cancel on the variation. If we're not varying the geometry,
No, just
that part will just not contribute. Then we can invoke, maybe at least for a CFT, we can invoke this argument that told us that the variation of the entanglement entropy is related to the variation of the energy density.
Yes.
But you could make a state whose energy density was negative inside the ball in quantum field theory. And so for such a variation of the state, you should have a decrease of the entanglement entropy in the ball.
By that conjecture.
Yeah, well, or by, no, even just by the cited relation between variation of the modular Hamiltonian and variation of the entanglement entropy. So the paper you're talking about might have sort of implicitly or explicitly assumed the energy density was positive.
Okay, interesting.
This derivation reminds me of the relative entropy derivation in Einstein's equations by Mark von Ramsdong, Brian. Is there a connection between your work and theirs?
Yeah, I think so. In fact, thank you for bringing that up. In fact, I was inspired to try this by their work. So using the CFT setting and the Ryuta-Yanagi formula, people have looked at variation, well, derived the Einstein equation for perturbations of anti-de Sitter space. basically from the story that I was telling here in the book, but applied in the CFT. There you have a CFT, and there's no gravity, and everything's under control. We can invoke this relation between the entropy variation and the energy density.
It's a boundary CFT.
Right,
It's not a bulk
exactly.
CFT.
Right, but then with the bulk boundary dictionary, it's exported into the bulk. For instance, Swingle and Van Ramsden exported the energy density into the bulk. And so you can derive the linearized Einstein equation around ADS. But I was thinking, what led me to this is I was thinking, well, shouldn't any CFT be, any quantum field theory be pretty much like a conformal field theory at very short scales? And don't I want to derive the Einstein equation in its full nonlinear glory, not just perturbing around ADS? And shouldn't these ideas work sort of locally? And that's the whole point.
Okay, let's think that again.